Download this code from codegive.com, link in the description below. Android Application Pinning Bypass, a deep dive, hack the box pinned. Android application pinning is a security mechanism implemented by developers to prevent man-in-the-middle (mitm) attacks and ensure that the application only communicates with its intended server. This is achieved by embedding the server's certificate, or its public key, within the application and comparing it with the certificate presented by the server during the TLS handshake. If the certificates don't match, the connection is refused, preventing attackers from intercepting or manipulating the communication. While effective, certificate pinning can be bypassed using various techniques. This tutorial provides a comprehensive overview of how to bypass application pinning on the Hack the Box Pinned challenge, covering both static analysis, dynamic instrumentation, and practical examples. We will use Frida and other tools to demonstrate the process. Understanding the target application, pinned, hack the box. The pinned hack the box challenge involves a vulnerable Android application that implements certificate pinning. To successfully solve the challenge, you'll need to intercept and modify the network traffic between the application and the server. The first step is to understand how the application implements pinning and identify the vulnerable areas. Assumptions ***. You have a rooted Android device or emulator, example Genymotion, Android Studio emulator, or a real device rooted with Magisk. You have ADB, Android Debug Bridge, installed and configured on your computer. You have Frida installed on your computer and the Frida server running on your Android device. You have a basic understanding of Java and Android development concepts. You have a basic understanding of network protocols, HTTP, TLS/SSL. You have basic scripting knowledge, Python, JavaScript. 2. Setting up your environment. 1. Install Frida ***. On your computer *pip install Frida tools. On your Android device download the appropriate Frida server binary for your device's architecture from https://github.com/frida/releases, https://github.com/frida/releases. Push it to your device and set execute permissions. Run Frida server on your device, via ADB shell, run the Frida server in the background. 2. Install ADB ***. Download and install the Android SDK platform tools to have ADB. Make sure it's in your system's path. 3. Install APK Analyzer, optional. Android Studio provides an APK analyzer that can be very helpful. Alternatively, use AppTool for decoding the APK. 4. Install a proxy, Burp Suite or OWASP Zap. Configure your Android device to route traffic through a proxy like Burp Suite or OWASP Zap. This will allow you to inspect the network traffic and modify requests and responses. Install the proxy's certificate on your device. You need to install the proxy's CA certificate as a trusted certificate on your Android device to prevent TLS errors when intercepting HTTPS traffic. This usually involves downloading the certificate from your proxy application, example Burp Suite CA certificate, and installing it through the Android system settings, security-encryption and credentials-install a certificate-CA certificate. On Android 7.0 and later, you may need to move the certificate to the system partition to trust it for all applications. This requires root. You can do this by renaming the certificate with a .0 extension and placing it in /system/etc/security/cassert/ and then rebooting the device. This step is critical for older versions of Android. Modern versions usually work without this step if the proxy is configured correctly. Configure the proxy on your device. Go to Wi-Fi settings, long press on your connected Wi-Fi network, select Modify Network, enable advanced options, set the proxy to manual, and enter the IP address and port of your proxy server, example 192.168.1.100:8080. 3. Static analysis, disassembling the APK. Before diving into dynamic instrumentation, let's perform static analysis to understand how the application implements certificate pinning. We'll use AppTool or Android Studio's APK Analyzer to examine the code. 1. Decode the APK*. 2. Examine Android manifest.xml*. Look for interesting permissions, services, or activities that might be related to networking or security. 3. Analyze SMLI code, the decompiled Java code. Identify key classes. Look for classes with names like Pinning Manager, Certificate Pinner, SSL Context Factory, Network Manager, or any class responsible for handling network connections. Search for keywords like Certificate, Pinning, SSL, TLS, Hostname Verifier, and Trust Manager. Inspect certificate loading. Check how the application loads the certificate, for pinning. Is it from a resource file within the APK, common, but less secure, or is it fetched from a remote source, more complex? Analyze pinning implementation. Examine the code that performs the actual certificate pinning logic. This usually involves creating an SSL context with a custom trust manager that validates the server's certificate against the pinned certificate. Look for comparisons between the server's certificate and the stored pin. Look for weaknesses. Are there any obvious vulnerabilities in the pinning implementation? For example, incomplete pinning. The application might only pin the root certificate authority, CA, instead of the entire certificate chain. This is generally considered weak because a compromised CA could issue certificates for the application's domain. Bypass mechanisms. The developer might have included debug code or conditional statements that disable pinning in certain scenarios, example for testing or development purposes. Insecure storage. The pinned certificate might be stored in an insecure location, example plain text in shared preferences. Example SMLI code snippet, illustrative. Let's assume you find code similar to this in a class called pinningmanager.smli. In this example, the application loads the pinned certificate from the asset/pin.crt file. It then creates an X509 trust manager that trusts only the certificate. This is a common pattern. A bypass will likely involve modifying the behavior of create trust manager method or altering the trust manager for certificates method. 4. Dynamic instrumentation with frida. Frida is a powerful dynamic instrumentation toolkit that allows you to inject JavaScript code into a running process and modify its behavior at runtime. We'll use frida to bypass the certificate pinning implemented by the pinned application. A. Identify the target method ***. Based on the static analysis, or by observing the application's behavior in Burp Suite, identify the method responsible for performing the certificate pinning. In the example above, it would be the createTrustManager method within the com_example.pin.pinningManager class and maybe the trust manager for certificates method as well. B. Write the frida script ***. The frida script will hook the target method and modify its behavior to bypass certificate pinning. There are several ways to do this. Disable pinning. The simplest approach is to prevent the application from loading the pinned certificate or to replace the custom trust manager with a default one that trusts all certificates. Asterisk trust all certificates. Asterisk modify the trust manager to always trust any certificate presented by the server. This is less secure but easier to implement. Asterisk pin Burp Suite certificate. Asterisk modify the trust manager to trust Burp Suite CA certificate. This allows you to intercept and inspect the traffic without breaking the application's pinning. Here are some example frida scripts demonstrating these approaches. 1. Disable pinning, simplest. This script disables the certificate pinning by replacing the custom trust manager with a trust manager that does nothing. This effectively trusts all certificates. Corrected disable pinning script asterisk. 2. Trust all certificates, more robust. This script creates a custom trust manager that trusts all certificates and then replaces the application's trust manager with this custom one. This is a more robust approach than simply returning null because it handles the case where the application expects a valid trust manager object. 3. Pin Burp Suite certificate, more secure. This script extracts Burp Suite CA certificate from a file. You need to export it from Burp Suite and push it to your device, and modifies the trust manager to trust only that certificate. This allows you to intercept traffic through Burp Suite without breaking the application's pinning. C. Run the frida script asterisk asterisk. 1. Save the frida script, example bypass _ pinning.js. 2. Run the application on your Android device / emulator. 3. Run the frida script against the application's process. First, find the application's process name using adb shell psgrep application _ package _ name. For example, this will give you the process ID and name. Let's assume the process name is com_example.pinned. 4. Execute the frida script asterisk. U connects to the USB device. F specifies the application package name to spawn. L specifies the path to the frida script. D. Verify the bypass asterisk. 1. Configure your proxy, Burp Suite or OWASP ZAP, to intercept traffic from your Android device. Make sure the proxy's CA certificate is properly installed on your device, as explained earlier. 2. Run the application and attempt to access the protected API endpoints. 3. Verify in Burp Suite, or OWASP ZAP, that you are now able to intercept and inspect the traffic between the application and the server. You should see the requests and responses passing through the proxy. V. Advanced techniques and considerations. Hostname verification Some applications also implement hostname verification, which checks if the hostname in the server's certificate matches the hostname the application is connecting to. You may need to bypass this as well by hooking the hostname verifier interface. Look for classes implementing javax.net.ssl.hostname verifier. Root detection Some applications implement root detection and may refuse to run on rooted devices. You may need to bypass root detection before you can use frida. This can involve hooking methods like runtime.getRuntime.exec, or checking for the existence of specific files, example /system/bin/su. Obfuscation applications can be obfuscated to make static analysis more difficult. Tools like DexGuard can be used for obfuscation. In these cases, dynamic instrumentation becomes even more crucial. You may need to experiment with different frida scripts to find the correct methods to hook. Anti-frida Some applications implement anti-frida techniques to prevent dynamic instrumentation. This might involve detecting the presence of the frida server or the frida agent. Bypassing anti-frida measures can be complex and may involve modifying the frida agent or the application's code. Techniques include Asterisk process name detection asterisk the app checks for Frida's process name. Rename Frida server on the device. Asterisk port scanning asterisk app checks common Frida ports. Use Frida listen equals 127.0.0.1 new underscore port and change the port the Frida server listens on. Asterisk thread name detection asterisk the app checks for Frida's thread names. This requires more sophisticated hooking, where you modify the app's thread.getName function to return a different name. Asterisk Kotlin coroutines asterisk if the application uses Kotlin coroutines for networking, the pinning logic might be implemented within the coroutine context. You may need to hook the coroutine dispatcher or the suspending functions that perform the network requests. Asterisk React Native / Flutter / other frameworks asterisk if the application is built using React Native, Flutter, or other cross-platform frameworks, the pinning logic might be implemented in JavaScript or Dart code. You'll need to use Frida's JavaScript or Dart support to hook the relevant functions. Asterisk OKHTTP and retrofit asterisk many Android apps use OKHTTP or retrofit libraries for networking. These libraries provide their own ways to implement certificate pinning. Therefore, you should target these libraries' functions for intercepting and bypassing the pinning. 6. Example, bypassing pinning in an OKHTTP application. Let's say the application uses OKHTTP for its network requests and implements pinning through OKHTTP certificate pinner. Here's an example Frida script to bypass this. This script hooks the build method of certificate pinner.builder and returns an empty certificate pinner, effectively disabling certificate pinning for OKHTTP. 7. Ethical considerations. This tutorial provides information for educational purposes only. Bypassing security measures without authorization is illegal and unethical. Only use these techniques on applications you own or have explicit permission to test. Always respect the terms of service and privacy policies of the applications you use. 8. Conclusion. Bypassing Android application pinning requires a combination of static analysis, dynamic instrumentation, and knowledge of the application's specific implementation. Frida is a powerful tool for dynamic instrumentation that can be used to hook methods, modify variables, and bypass security measures. However, it's important to be aware of the legal and ethical implications of these techniques and to use them responsibly. This tutorial provides a starting point for understanding and bypassing certificate pinning, but the specific steps required will vary depending on the application. The Pinned Hack the Box Challenge provides an excellent opportunity to practice these techniques in a safe and controlled environment. Remember to continually update your skills and knowledge as security techniques evolve. Good luck.